Okay, so we're looking at parametric equations in conics. We've seen all of conics with Cartesian, and the idea is that Cartesian's asked most of the time, but parametric obviously can come up. So let's start with circles. We know that x squared plus y squared equals r squared is our Cartesian equation for a circle. However, if we want to write it in parametric form, it's what's in red there. So x equals r cos theta and y equals r sine theta. And you can see there by my diagram on the unit circle, we know this already because we know that the x coordinate on our unit circle is thinking of r being the radius of that circle, r cos theta, and the y coordinate is r sine theta, the length and the height of that particular point. So it's just about remembering those parametric equations for a circle there in red. What we look at now, though, is the tangent and normal, just as we looked at tangent and normals when it came to our Cartesian equation. Let's think back to finding tangents and normals. To find a tangent or a normal, we would normally differentiate, sub in the point if we need to, and then use our point gradient formula. So it's no different. Okay, so it's just about, okay, well, differentiate, sub in our value, and sub it into our point gradient formula. So I can do this in a few different ways, but let's just have a look at what would happen if I differentiated my original equation of a circle. I'm going to have to do implicit differentiation because we've got x's and y's. So if I differentiate my equation of a circle, I'm going to have 2x plus 2y timesing by dy on dx, which is equal to 0 because r is just a constant. So I'm going to have that dy on dx is equal to minus 2x divided by 2y. So dy on dx is equal to minus x on y. So now I sub in my point, and that will turn this into the gradient of my tangent. My x value in parametric form is r cos theta, and it's negative x over my r sine theta, which is going to cancel my r's, and I'm going to get negative cos theta on sine theta as my gradient of my tangent. Now, I could also write that as 1 over tan or negative cot, but I'm going to leave it in cos and sine. Usually cos and sine is a nicer form. If I wanted my gradient of my normal at this point, I would just take the negative reciprocal. So my gradient of my normal would be just sine over cos, which I could write as tan. But let's stick with our tangent for now. I found the gradient of my tangent. Now I just sub it into my point gradient formula. Y minus my y value, and my y value being r sine theta, is equal to my gradient of my tangent, x minus r cos theta. When we're using our point gradient formula, at any time, if you have a denominator out here, we times it on the other side by both terms on the other side. So I'm going to get y sine theta minus r sine squared theta is equal to, and now expand out my negative cos, negative x cos theta plus r cos squared theta. I'm going to take over and have my squareds on one side and my other ones on the other side, which is going to give me y sine theta plus x cos theta is equal to r, and I'm going to just do 2 steps here, factorize out the r, my sine will come over and become a positive. Now I know that sine squared theta and cos squared theta plus in together is 1. So I end up with the equation y sine theta plus x cos theta is equal to r. The official formula for the tangent to a circle in parametric form is in fact this. And you can see that all they've done is times everything by r, and that's the official formula. So if you had to find the equation of the tangent, either one of these two are fine. So if you were doing the normal, all you would be doing is substituting in your value for your gradient of your normal in where the gradient was and doing the exact same process. So there we have it. Either one of those is fine, and it's the equation of our tangent to the circle in parametric form. Okay, let's move on to our most iconic conic, and that is the ellipse. So let's think about our ellipse. We know that in Cartesian form, our ellipse has the formula x squared on a squared plus y squared on b squared is equal to r squared. Oh, sorry, thinking about a circle, is equal to 1. All right, parametric form. Again, we can remember these, we don't have to prove them. X equals a cos theta and y equals b sine theta. All right, so that's our parametric form for an ellipse. Now, if a question asks you to prove that certain parametric equations satisfy an ellipse, it's just about, and this comes up a lot, which is why I'm mentioning it, just subbing in your x value of your parametric equation. I'm going to get x squared, so a squared cos squared theta on a squared, plus b squared sine squared theta on b squared is equal to 1. My a squared and b squared will cancel, which gives me that cos squared theta plus sine squared theta equals 1, which is true by the Pythagorean identity. Okay, let's look at our tangents and normals though. When this stops doing this. All right. Tangents and normals of an ellipse. Let's start with our parametric form. And I could have started with my parametric form in a circle as well. You would still get the same answer. It's more common to start with your parametric form because we're dealing with parametric equations in this particular lesson. So again, to find the equation of a tangent, I differentiate. I'm going to differentiate both of these. So this first one is derivative of x with respect to theta. And I'm going to get negative a sine theta. Then the next one is the derivative of y with respect to theta. And I'm going to get b cos theta. Now the thing is though, to differentiate and then say that's our gradient of our tangent, we need dy dx. That's the gradient function. So think about how I can get dy dx, and that's with my chain rule. If I take dy d theta and I multiply it by d theta on dx, which is just the reciprocal of dx on d theta, I would get it. So therefore I can say it's dy dx, my gradient function, is just going to be b cos theta timesing by 1 over negative a sine theta, which is just going to give me negative b cos theta all on a sine theta. And there's my gradient of my tangent. Okay, now if I wanted the normal, take the negative reciprocal. I'd have A sine theta over B cos theta. Alright, now once I've got my gradient, we go to our point gradient formula. My y value is just going to be B sine theta. My gradient I just found. And my x value is A cos theta. Alright, once again, if you have a denominator, times it over the other side. So I'm going to have AY sine theta minus AB sine squared theta is equal to, expand this out also, minus BX cos theta, oops, plus AB cos squared theta. Get all my squares on one side. I'm going to have AY sine theta plus BX cos theta is equal to AB, and do this in one step again, factorise it out, plus sine squared theta. Okay, then I'm going to have AY sine theta plus BX cos theta is equal to AB, lots of 1, divide by my AB, okay, and my A will cancel with my A and my B will cancel with my B, so I'm going to end up with Y sine theta on B plus X cos theta on A is equal to 1, and that is the equation of the tangent to the ellipse. Now once again, if I wanted the equation of my normal, I would do the exact same thing, but I would sub in. Why is it doing that? Anyway, I would just sub in my gradient of my normal instead. Okay, let's keep moving. Next, we've got the hyperbola. Okay, our hyperbola, we know we have the equation of x squared on a squared minus y squared on b squared is equal to 1. In parametric, I'm going to get that x is equal to a sec theta and y is equal to b tan theta. So again, remember those. They are the parametric equations for a hyperbola. Alright, tangents and normals. Once again, start with your parametric. The derivative of x with respect to theta. Derivative of sec, that's on your reference sheet. Otherwise, it's not hard to remember. It's just this. Derivative of y with respect to theta. We know that that's just b sec squared theta. So once again, my dy dx is what I need for the gradient function. And I'm going to get that by taking dy on d theta and multiplying it by d theta on dx. Which is going to give me that, therefore, dy dx is equal to b sec squared theta timesing by 1 over a sec theta tan theta. 1 sec will cancel one of them, and I'm just going to be left with b sec theta all over a tan theta. And there's my gradient of my tangent. My gradient of my normal is just going to be negative a tan theta over b sec theta. Okay, so now to find the equation, I'm going to go to my point gradient formula. Y minus y1 is equal to m lots of x minus x1. And the same idea, I'm going to do the equation of the tangent. I'm going to have y minus my y value, which is b tan theta. And that's equal to the gradient I got, b sec theta on a tan theta. X lots of x minusing with a sec theta. Again, multiply your denominator over and expand your brackets as well. I'm going to have a y tan theta minus a b tan squared theta, and that's equal to bx sec theta minus ab sec squared theta. Get my squares on one side. I get a y tan theta minusing bx sec theta, and that's equal to negative ab sec theta squared plusing with ab tan squared theta. Now, if I factorise out a negative ab here, I get a positive sec squared and a negative tan squared. And the reason I've done that is one of your other Pythagorean identities. If it doesn't look familiar, you need to go back and look at your 3 Pythagorean identities. But it also equals 1. So now I'm going to have that a y tan theta minus bx sec theta. Divide that by your negative ab. Or technically, let's make my life a bit easier, divide each one individually. And that's going to be equal to 1, because this term here is just equal to 1. An a will cancel with an a, and I get, let's write this in the other way, b will cancel with a b, and my negative will cancel with a negative. So I'm going to have x sec theta on a, this one's the negative now, minus y tan theta on b, and that's equal to 1. And that is the equation of the tangent to a hyperbola. Again, you want your normal, all you're going to do is sub in the equation of the gradient of your normal into where m is and do the exact same thing. Okay, and the very last thing I wanted to look at, so we've done circle, we've done ellipse, and we've done hyperbola. The last thing, which doesn't come up too often, is your rectangular hyperbola. So let's just go in here. Rectangular hyperbola. If you can't remember, you need to go back and have a look. But our Cartesian equation for a rectangular hyperbola is xy equals c squared. Now your rectangular hyperbola is the ones that we always saw the most of in junior school. It actually has asymptotes that bisect at right angles. That's the definition of it. Okay, and we normally see it as y equals 1 on x, say. But if you think about it, if I times my x over, I get xy equals 1. Okay, which is then in this form. So it is actually the one that looks most unfamiliar, but it is the most familiar. So our Cartesian equation, so again, another one to remember, x is equal to ct and y is equal to c on t. Start with your Cartesian equations and differentiate. Now think though, it may be confusing, okay, what do I differentiate in terms of? and what's a constant, what's not a constant, you're going to differentiate this in terms of t. Okay, so that means that t is the letter and c is a constant, which means if that was 2x, it would be 2 when I differentiate it. So ct becomes c. C over t is really ct to the power of negative 1, which when I differentiate that with respect to t, times it out front, subtract 1 from the power, I'm going to get negative ct to the power of negative 2, which is the same thing as on t squared. Now, same thing, to get my gradient function, I need dy on dx, which is going to get me that by doing dy on dt with my chain rule, timesing by dt on dx. So now, therefore, my gradient function is going to be negative c on t squared, timesing by 1 on c. My c's will cancel, and I end up with a gradient of my tangent being negative 1 on t squared. So my gradient of my normal, if we needed that, would be just t squared. Okay. Now we want the equation. So once again, we just take our gradient and we sub it in and we get the equation. So if we take y minus y1 equals m lots of x minus x1, y minus my y value, c on t, equals negative 1 on t squared, x minus my x value, which is ct. Again, times my t squared over and expand out my negative 1. I'm going to have t squared y minus ct equals negative x plus ct. Clean this up a bit, I'm going to have x plus t squared y is equal to 2ct. And there is the equation of my tangent in parametric form of my rectangular hyperbola. If you want your normal, all you would do is sub in t squared in where m is and rearrange for that instead. Okay. My next video, I'm going to be putting all of these proofs now into example questions. So HSC style questions and how you use them and what you do.